Hello everyone, my name is Patricio and I am a researcher from UECE, the State University of Ceará, here in Fortaleza, Brazil. I'm here to present our work on malware detection in Windows operating systems using AI and in-memory process analysis. This research was developed by myself, Patricio, Carlos Paiva, Renan Rodrigues, and Vanessa Lima. It was conducted under the supervision of Professor Dr. Rafael Gomes from UES. Here is our presentation roadmap. I will cover the context and motivation behind this research, our proposed solution and its architecture, the methodology we employed, the experiments and results we obtained, the industrial impact and business value of this approach, and finally, our conclusion and future work. Let me start with the context. Currently, there is a notable and significant increase in concern regarding cybersecurity of both corporate and personal data. This is driven by the continuous rise of advanced malicious software, including spyware, trojans, and ransomware. Windows operating systems continue to be one of the primary targets for malware attacks. Now, the main technical challenge we face today is the proliferation of what we call fileless malware. It lives entirely in the computer's RAM memory, never touching the disk. This makes traditional detection methods based on file scanning completely ineffective. To detect fileless malware, we must use a different approach, in-memory inspection, also known as memory forensics. However, in-memory inspection introduces a severe technical challenge that has prevented widespread adoption in enterprise environments. The traditional approach requires generating what we call a full memory dump. A memory dump is essentially a complete snapshot of everything stored in RAM at a given moment. For a typical enterprise workstation with 8 gigabytes of RAM, the memory dump file is approximately 8 gigabytes in size. For modern systems with 16 or 32 gigabytes of RAM, you can imagine the magnitude of the problem. Now consider the scenario. You need to monitor hundreds of thousands of endpoints across your enterprise network. Each endpoint must periodically extract its memory dump, send this multi-gigabyte file over the corporate network, and wait for a centralized server to analyze it. This creates what we call a severe I/O overhead. The network bandwidth consumption becomes prohibitive. The storage requirements grow exponentially, and the time required to transfer and analyze each dump makes real-time detection practically impossible. This is the scalability bottleneck that our research aims to solve. Given this context, our research objective was clear. We need to engineer a dependable system that is low overhead, portable, scalable, and fast enough to detect malware in real time. To ensure our solution would work in real-world conditions, this research was validated in partnership with CPDI, the Centro de Pesquisa, Desenvolvimento e Inovação. This validation confirms the practical relevance and real-world applicability of our solution. We designed an intelligent malware detection solution for Windows operating systems that leverages artificial intelligence and in-memory process analysis. We create what we call a device service model. This is a segmented architecture that divides responsibilities between two distinct components. The device component runs directly on the client machine, the endpoint we want to monitor. The device component is responsible for just three main tasks. First, it extracts the raw memory dump using a tool called WIMP-man. Second, it compresses this memory dump file using a library called zip-file. Third, it securely transmits the compressed file to the service component for analysis. This keeps the impact on the monitored device absolutely minimal. The service component runs on a centralized server, typically in an edge computing environment or a data center. The service component is responsible for, first, receiving and decompressing the memory dump files sent by monitor devices. Second, performing feature extraction. We use a tool called Vulneralizer, which is built on top of Volatility Framework. Third, applying trained AI models to classify the extracted features. The AI models determine whether the observed behavior is benign or malicious. Fourth, storing all data for audition purpose and future model retraining. And finally, sending the classification result back to the device component, which can then execute appropriate containment actions if malware is detected. We use exclusively open source libraries, including PowerShell, Python, Wimpyman, Vulneralizer, Docker, Postgres, and Flask. The device component is implemented using PowerShell and Python scripts. The operation follows these steps. Step 1. The script extracts the raw memory dump using Wimpyman. Step 2. The script compresses this file using the zip file library. Step 3. The compressed file is transmitted to the service component via HTTPS with TLS encryption. Step 4. The device component monitors the analysis status. Step 5. Once analysis is complete, the device component receives the classification result. Step 6. Based on the classification, the device component can execute mitigation actions. The entire process is automated through Task Scheduler on Windows. The service component consists of Docker containers running a Flask web server and a Postgres database. When the service receives a compressed memory dump, it follows this workflow. Step 1. Decompress the received file to recover the original raw format memory dump. Step 2. Launch Vulneralizer to analyze the memory dump. Step 3. The extracted features are formatted into a feature vector and passed to the AI classification modules. Step 4. The trained machine learning models analyze the feature vector and produce a classification, either benign or malicious. Step 5. All data is stored in the Postgres database. The complete technology stack includes Windows 10 compatibility on the client side and on the server side, Python for scripting and data processing, Flask for the web API, Docker for containerization, Postgres for data persistence, and Vulneralizer with volatility for memory forensics. The diagram shows the complete execution flow connecting all components I just described. You can see the cycle: extraction, compression, transmission, decompression, future extraction, classification, and result delivery. The cycle repeats periodically, for example, every 30 minutes, on each monitored device, ensuring continuous protection. Now let's move to the experimental validation. We conduct three key experiments to validate different aspects of our system. The first experiment focused on memory extraction efficiency. The objective of the experiment was to evaluate and compare the efficiency of different RAM memory dump tools. Specifically, we compared two popular tools, Dumpit and Wimpyman. We measured two metrics: extraction time, how long it takes to create the memory dump file, and analysis time, how long Normalizer takes to process the dump. Looking at the results table, for the 2 GB configuration, Wimpyman required only 6 seconds, plus or minus 0.6 seconds for extraction. In contrast, dumpage requires 60 seconds plus or minus 1.8 seconds. That's almost 3 times lower. 4 gigabytes Wimpman took 23 seconds plus or minus 2.1 seconds, while dumped took 62 seconds plus or minus 8.1 seconds. For 8 gigabytes, Wimpman took 88 seconds plus or minus 7 seconds, while dumped required 235 seconds plus or minus 23.5 seconds. The pattern is clear. The Wimpman consistently outperforms dumped across all rank configurations. Based on these results, Wimpman was selected for our solution. The decision was based on two factors: superior extraction speed and its open source nature, which aligns with our design principles. The second experiment addressed the data compression challenge. The objective of this experiment was to evaluate different compression methods and find the optimal balance between compression ratio and execution time. Looking at the results table, the LZMA-based methods achieved the highest compression ratio as 77.94%. This is impressive compression. However, look at the execution times. 660.19 seconds. That's more than 11 minutes. Tarfile plus LZMA was even slower, at 702.91 seconds, almost 12 minutes. For a solution that needs to run periodically on potentially thousands of endpoints, these execution times are completely unacceptable. This will create exactly the kind of performance impact we're trying to avoid. The zip file library, however, provides the best balance. It achieved 69.94% compression, nearly as good as the LZMA methods, in only 131.9 seconds. That's just over 2 minutes. Based on the analysis, zip file was selected as a compression solution. This choice enables approximately 60% reduction in data communication volume. Let me emphasize why this is so important. 60% reduction means that instead of transmitting an 8 gigabyte dump, we transmit only about 3.2 gigabytes. Instead of 16 gigabytes dump, we transmit about 6.4 gigabytes. This reduction is absolutely critical for system scalability. It dramatically decreases network bandwidth consumption, transmission time, and storage requirements on the service side. Without this compression optimization, our architecture would not be viable for real-world enterprise deployments. The third experiment focused on the core question: can we actually detect malware with high accuracy and low latency? The objective was to evaluate classification performance using machine learning algorithms and validate that our approach can meet the time-sensitive requirements of an industrial response system. The models were trained using the Malware dataset. This dataset was specifically created for memory-based malware detection research. It contains 9,996 balanced samples. Balanced means the dataset has 4,998 benign process samples and 4,998 malicious process samples. The malicious samples represent three distinct malware families: Trojan Grafter, Backdoor Cobalt, and Trojan Hawk. These are real-world malware families with different attack behaviors and evasion techniques. Now let's examine the results on the 20% test set. The solution achieved an overall detection efficiency of approximately 99%. All four algorithms demonstrated strong performance. However, the CART model provides the optimal balance for our use case. Why? Because CART achieves 95% accuracy, which is excellent, while maintaining the absolute lowest inference latency at 15.66 milliseconds. This speed is crucial. Remember that in an enterprise environment, you might be monitoring hundreds of thousands of endpoints. Each endpoint generates periodic memory dumps that need to be classified. If classification takes even 100 milliseconds per sample, the system can quickly become a bottleneck. But at 15 milliseconds per sample, a single service instance can easily handle dozens of concurrent classification requests. This low latency is essential for meeting the time-sensitive requirements of an automated response system where rapid detection and immediate containment are critical. However, I must emphasize a critical limitation. These results reflect performance on the controlled, balanced moment dataset. The moment dataset has a 50-50 split, 50% benign samples, 50% malicious samples. But real-world enterprise environments look very different. In production systems, the class distribution is heavily imbalanced. Approximately 90% of processes are benign and only about 10% are malicious. Additionally, the moment dataset contains only three malware families. Real-world environments encounter hundreds or thousands of different malware variants, including brand-new zero-day threats that have never been seen before. Therefore, while our results are promising, real-world deployment will require addressing class imbalance through techniques like weight loss functions or sampling strategies, and continuous model retraining as new malware variants are discovered and labeled. Now let's discuss the industrial impact and business value of the solution. Operational expense reduction. The 60% data compression we achieve has direct economic implications. At scale, this 60% reduction translates directly to lower network infrastructure costs, you need less bandwidth capacity, lower storage costs, you need fewer storage arrays, and lower operational costs, less time spent managing network congestion and storage expansion. The solution becomes economically viable for large-scale deployments, specifically because we've eliminated the data transfer bottleneck. Dependable real-time response. The approximately 99% detection accuracy combined with millisecond response times enables what we call near real-time threat mitigation, specifically with the CART model providing 15.66 millisecond classification latency. The total time from memory dump extraction to threat detection can be measured in seconds rather than hours. This capability is critical for reducing the mean time to respond, or MTTR. Our solution can detect fileless threats within minutes of their execution in memory. This rapid detection is essential for maintaining business continuity and minimizing damage from security incidents. Scalability. The modular design of our device service architecture enables what we called horizontal scaling. This architectural approach was validated in partnership with CPDI using environments that simulate the client deployments. Deployment viability. The solution's compatibility with Windows 10 environments and its use of open source technology stack eliminates what we call vendor lock-in. Finally, the minimal user intervention requirements achieved through automated scheduling reduces operational burden on IT security teams. Once deployed, the system runs continuously without manual oversight. To conclude, let me summarize our key contributions. We successfully developed an AI-driven memory analysis solution for Windows malware detection. This solution prioritizes both scalability and minimal user impact, two requirements that are often in tension with each other. We overcame the I/O bottleneck that has prevented widespread adoption of memory forensics in enterprise environments. We achieved this through effective data compression of over 60%, validating the system efficiency and scalability in realistic test environments. We achieved high detection efficacy, above 95% across all tested algorithms, with the CART model providing optimal performance for time-sensitive requirements at 15.66 milliseconds per classification. We validated the practical applicability of this approach through an industrial partnership with CPDI using test environments that mirror real client configurations. However, I want to emphasize again the important limitation of this work. Our results are based on the balanced moment dataset. Real-world deployment will need to address two significant challenges. First, class imbalance constraints. Production environments have approximately 90% benign and 10% malicious samples, not the 50-50 split we trained on. This imbalance can reduce model performance and increase false positives. Second, data diversity and novel malware variants. The Malware dataset contains only three malware families. Production environments encounter constant evolution of malware techniques and entirely new attack methods. Continuously model retraining will be essential. These challenges are addressable through established machine learning techniques, but they represent important future work. Speaking of future work, we have identified two major areas for continued development. First, containment module. We plan to integrate a complete containment mechanism that can automate specific defensive actions immediately following malware classification. These actions might include isolating the infected process from network resources, terminating the malicious process, quarantine the entire system from the corporate network, or alerting security administrators for manual investigation. Second, observability. We plan to develop a user monitoring panel, essentially a dashboard, that provides real-time visualization of key system telemetry. Thank you very much for your time and attention. I am now ready for your questions.